and I have made a fairly extensive survey, not a deep survey, but fairly extensive, of the various approaches. In particular, I mentioned the possibility of computing Valrasian equilibria following Scarf and others, and his algorithm, his type of algorithm, has found many applications, as I told you. I would like to discuss now a different problem. Once you know that there is an equilibrium, that you can compute it, you are, of course, pleased, but it would be marvelous if you could give conditions on the economy that would ensure that there is only one equilibrium. Then the theory would be completely determinate. And the search for uniqueness has gone on for decades without much success, except if you have results of the type described in the first half of my last lecture, at the end, the type of result that Werner Hildenbrand obtained. However, it is perfectly reasonable to have more limited ambitions and to ask not for global uniqueness, but for local uniqueness of equilibria. That is what I want to discuss now, especially since I finished work on that problem in New Zealand in 1969. Let E be a complete description of the economy. That is to say, all the parameters necessary to describe the economy. That would include a specification of the endowments, of the demand functions, etc., etc. And I will denote by script E the set of all the economies that you consider in the model. For instance, you may want the demand functions to be continuous, differentiable, so that will restrict small e in different ways. E is the set of all the possible economies you will consider. Let now S be the set of possible states of the economy, and for instance, a state of an economy in this model would be a listing of all the consumption vectors of all the prices prevailing in the economy. And so you can say in a very symbolic way that given an economy in the set script E, if S is the set of states, the set of equilibrium states will be a subset of S that will depend on small e. In general, the equilibrium is not unique, and therefore we have a set Roman E of small e, which in the best circumstances will be finite. And of course, even possibly unique. What we have talked about is conditions ensuring that the set of equilibria is not empty. I now want to illustrate in the Edgeworth box the difficulties we have to confront. That is the simplest prototype of an economy. There are two commodities and two consumers, and you have, if the, I assume here a knowledge of the Edgeworth box. For those of you who don't know it, close your ears for a few minutes. You have an equilibrium if a situation like this prevails. This is the origin, this is the vector of total resources, this is the vector of resources for the first consumer, and you have an equilibrium if the two indifference curves are tangent to each other and if the common tangent goes through the point E. Now it is perfectly easy to construct examples in which you have a continuum of equilibria. That is, for any one of the points here, you have a common tangent that goes through E, something like this. As you see, you can construct examples like this at will. That is one of the beauties of the Edgeworth box, that in this very simple geometric situation, you can indeed get easily counterexamples to the conjecture, for instance, that an economy typically always has finitely many equilibria. It is not true. Here you can construct an example of an economy with a continuum of equilibria, and mind you, the preference relations that you construct here can be as regular as you like. They can be infinitely, continuously differentiable, representable by concave functions, etc., etc. In spite of that, you may have this very nasty situation. So the problem you are facing is quite different from the problem of existence, because in the case of existence, you could specify conditions on the endowments, on the preferences of the consumers separately, ensuring that there would be at least one equilibrium. Here, no matter how well behaved mathematically the various consumers are, you may have this nasty situation. It is unavoidable. So the best that you can hope is to prove that for almost any small e in the Edgeworth box, given the preferences of the two consumers, you will have local uniqueness of equilibria. And that is precisely what I want to do. For this, you will have to use some differential topology, and very specifically the theorem of Sard, which I will give you in different forms with increasing generality. It has been characterized by a great mathematician as one of the three main results of analysis. The mathematician in question is René Thom. So let me illustrate what Sard theorem has to say. First of all, in the case of a function f from the reals to the reals, and we assume that f is continuously differentiable, so it will be, for instance, something like this. A very simple function. You say that a point x is critical if f prime of x is equal to 0. If the derivative with respect to x is equal to 0 in this particular case. That is a critical point. And you say that y is a critical value if y is the image of a critical point. And if you look at a situation like this, where we have a plateau, horizontal, you see that the set of critical points can be very large indeed. Take the extreme case of a constant function, then the set of critical points will be the entire set. However, the set of critical values is small. In the picture I have drawn here, there are only two, namely this point and this point. And that is what Sard theorem is about. It tells you that the set of critical values has Lebesgue measure 0. In this particular case, I will discuss generalizations. So Lebesgue measure 0, which, if one does not want to use measure theory, says that you can cover the set of critical points with a countable set of intervals, and the sum of the lengths of the intervals can be made as small as you like. The theorem of Sard, which is already not trivial in the case of function f from R to R, would be true as well if you took a function from Rn to Rn. If you like, you can restrict yourself to an open subset. It does not matter. But you have a function from Rn to Rn, let us say f. Naturally, now you have to use the Jacobian of f. And if the determinant of the Jacobian is equal to 0, you say that you have a critical point for the function. Similarly, a critical value is the image of a critical point. I emphasize that if you have a point y here in the image space, which is a critical value, it may be the image of several points here, and it is quite possible that many of them will not be critical points. But if one is, that is sufficient. If a point y is not critical, we say that it is regular. And so, in this context, the image from a space of dimension n to a space of dimension n and a function f that is C1, you have the same result. The set of critical values has Lebesgue measure 0. You can have a still more general situation, and in fact we need it in the economic application that we have in mind. And for this, you have to consider a differentiable manifold M and a differentiable manifold N. The general definition of a manifold I will give here is that you have in Rn a set of points such that if you take any point here, then you can, in a neighborhood of M, have a differentiable isomorphism between the intersection of M and that neighborhood and the intersection of a linear manifold of dimension small m, let us say, and that will define a manifold of dimension small m, and the origin. So you may have a manifold of dimension 1, 2, whatever you say. M can take any one of those values. And if you can put this geometrical situation, that is to say the origin, a linear manifold, a neighborhood of the origin, in a differentiable isomorphism with what happens here for every point, then M is a differentiable manifold. And now, if M and N are two differentiable manifolds of the same dimension, and if you have a function f from M to N that is C1, then Sard theorem tells you that the set of critical values, subset of N, is of Lebesgue measure 0. So those are the mathematical preliminaries, which are, of course, completely standard to differential topologists and were not known to economists until the fairly recent past. Are there any question on this? Let us apply this to the economic situation that we have in mind and try to give an intuitive account of the question of local uniqueness in differentiable economies. Sard theorem can be extended to cases in which the two manifolds are not of the same dimension, but we are not going to need that, so I don't give you the most general statement. Sard theorem can be extended to infinite dimensional spaces, but that we won't use either. So let our exchange economy be the prototype that we have discussed in the past. We have L commodities, and we have, let us say, M consumers. I try to be consistent in my notation. M consumers. And each one of them is described by an endowment vector in RL that will be E1 for the first, E2 for the second, EM for the last. And I will denote this list of vectors by E, which therefore has dimension L times M. Each one of these consumers has a certain demand function, and I will assume that the demand functions are fixed, simply to keep mathematics as simple as possible. There are extensions, of course, to the case in which the demand functions vary as well as the endowments. I want to present the simplest possible case. A demand function for consumer I is simply of the following form. It associates with a price vector P and a number W, representing the budget constraint, a certain demanded vector in RL plus, and we assume that we always have this equality P dot Fi of P and W equal to W, which means, as you remember, that if this is the budget hyperplane, then the consumer, although he is restricted to the shaded set, will in fact choose a demand that will be in the budget hyperplane. And the function Fi is assumed here to be continuously differentiable, that is to say, of class C1. Therefore, our economy, since those are fixed, is completely described by this list of L vectors. And in the notation I have introduced earlier, the set script E of economies is indeed the set of the small e that correspond to this definition. The dimension of E, script E, is L times M. One has to keep track of dimensions carefully since when we'll have to make sure that the two manifolds to which I alluded before are the same dimension. A state of the economy can be described by the price vector P, because once the price vector is known, if you have here a given demand function, then Fi of P, comma, P dot I gives you in a unique manner the consumption vector of the I's consumer. When P is known, all the consumption vectors of the consumers are known. Consequently, the state of the economy can be described just by the vector P. We will restrict P, which in principle could be non-negative. We will restrict it to be strictly positive, because we don't want to have problems with what happens at the boundary. The boundary can be taken care of. I will give you a general reference to this area a little later. And as I have said several times already, one can normalize the price vector in an arbitrary fashion, and we normalize it here in such a way that P belongs to S, the strictly positive part of the unit sphere. So we have in RL plus the unit sphere, and S is the strictly positive part. So the dimension of S is L minus 1. Dimension of the space minus 1, of course, the dimension of the sphere. And given P in S, there results for each consumer a demand, which is the vector I have written here. For the I's consumer, his or her excess demand is this vector minus EI, and the aggregate excess demand for the entire economy is obtained by making the sum over all the consumers. I call this capital F, which is a function of E and P, and there you are. Well, that is a vector in RL, which is well defined when E and P are specified. So given P in S, the set given E, the set of equilibrium P satisfies F of E and P equals 0. So symbolically, we have this situation. Here is the set script E. Here is the set S. And for a given E, we have here the set of equilibrium price vectors. If we consider the manifold M in E cross S, which is defined by this equation, then it will be shaped something like this. This is the manifold M. If all the functions fi are C1, capital F is C1, and there you have this M defined like this. What is the dimension of M? We have for every P, P dot Fe of P is equal to 0. That is Walras law. Consequently, here you have L conditions, but in fact L minus 1, because it's always satisfied. So the dimension of the manifold M is the dimension of V plus the dimension of S minus the number of restrictions. So that is the dimension of E, which we have said is L times M, plus L minus 1, and L minus 1 being the dimension of S. And we have to subtract the number of restrictions, that is minus L minus 1 for these. So altogether you are left with the dimension of M, which is equal to L times M. And consequently, the dimension of the manifold M is equal to the dimension of E. We are, of course, operating in spaces of high dimension here, high dimensions. So you have to stretch your intuition as much as you can, but there is no doubt this equality is correct. Now, we define, you remember our image of the two manifolds and the function from one to the other. What are they here? The first manifold is M. The second manifold is E, script E, and the function from M to E is extremely simple. It is the projection from M into E. Let us call it T for transformation. So you have here the projection T, and we associate with any point in the equilibrium manifold an economy E by projection. That is to say, if you consider a pair EP, then very simply the image of EP is E. Now surely capital T, considered as a function from M into E, is a differentiable function, trivially. So we are in the situation that we were dreaming of. We have a differentiable manifold M, a differentiable manifold E of the same dimension, and this function from M to script E, which is C1. So this tells us that Sartre's theorem applies, and the set of critical E's is of Lebesgue measure 0. The set of critical economies in this sense is of Lebesgue measure 0, is negligible in that sense. It is not yet a very satisfactory sense in which for a set to be negligible, but I will give a stronger statement a little later. And that means, of course, that a critical economy is an economy for which you have the determinant of a Jacobian equal to 0. You could say in a very intuitive geometric language that at a given point of M, you have a tangent hyperplane, and when the tangent hyperplane becomes vertical, then you have a critical economy. Let me elaborate a little. on this equilibrium manifold. So for instance, I will have here a positive vertical part. If you take an arbitrary economy here, then you have all these equilibria. You can show that if E is regular, if the economy is regular, non-critical, then the number of these points under very general conditions is odd. That goes back, in a sense, to Alfred Marshall, who did not consider this general situation, but the remark that you have generally an odd number of equilibria can be found already in Alfred Marshall in a much simpler context. Now, this is serious topology, differential topology. The statement that you have an odd number of equilibria is as a side interest in that, of course, it shows that you have for a generic, for a regular economy, generically, you have certainly at least one, since 0 is not an odd number. So there is an existence theorem contained in this. It is of some interest to see what happens, and the mathematics behind this is the mathematics of catastrophe theory. This is not really catastrophe theory because I do not have a dynamic model. I don't intend to present one. If E varies continuously, then when you reach a critical economy like this one or this one, then very unpleasant things may occur. If, for instance, this is the equilibrium that you are observing in your system, as the economy varies continuously, when you reach this point, then there is no choice, but the only equilibrium will have to be on this branch. So you have a very sudden jump. And similarly, of course, if you moved in this manner, then you might lose uniqueness, have a continuum, even locally. And if you go farther to the left, then you have to jump to this branch. So there are inherent discontinuities in this model. I have said earlier that in general, if you have a set of economies, an economy here, and the set of states, and the set of equilibria, E of E, then in the language that we are now using, we have a critical set, which I will call C, which has Lebesgue measure 0. And if you are outside of the critical set, then you have a set of equilibria, locally, each one of them locally unique. And what is important is that in the neighborhood of E, this set varies continuously in the sense of the continuity of correspondences. And that surely is extremely important because we can never measure exactly the various parameters appearing in the economy if the theory has any explanatory power, it has to be robust with respect to small changes in the values of the parameters, which is why regular economies are so important. here again the definition of the equilibrium manifold. Let me introduce a further assumption that will enable us to say more about the set of critical economies. When the price vector tends to the boundary of S, and that means that some prices become zero, let us assume that f of E and P is not bounded in norm. I phrase it in the most general possible way, which means in simple economic language that when some prices become zero, demand tends to become very large. And if you have a condition of this type, then you can say that the set C is closed. You see, to say that a set is of Lebesgue measure 0 is not in itself so interesting. If you take the real line, takes, if you wish, an interval, if you take the set of the rational points, that is a set of Lebesgue measure 0. And yet, to say that every economy except that set is regular, acceptable, is not very interesting, since the rational points are everywhere dense. So things are a little better if you can say that the set C not only has Lebesgue measure 0, but is also closed. And that is true in the case that we are now discussing. It also follows that then the set capital E of E, the set of equilibria, will be not only discrete, that is to say will have local uniqueness, in fact it will be finite. And so we have here too a much more satisfactory solution. We have a finite number of points, which in fact is an odd number, as I have hinted before. And finally, if you take an economy that is not in the critical set, then it has a neighborhood in which the set E of E, made up of finitely many points, is such that every one of those varies in a continuously differentiable manner with respect to E. That is a simple application of the inverse function theorem. Well, that is a very rough summary of what you can do with differential topology in this context. The generalizations have been numerous. In particular, you can, in addition to the list of the endowment vectors E, you can let the individual functions vary. Clearly, then, the mathematics become more sophisticated. It has been done. The area of research covered by the study of the generic, that is to say almost everywhere in the precise sense I gave you, the study of generically regular economies has been covered in a book by Andreu Mascolei, which appears in the references given to you in the past. Are there any questions on this topic? As I promised, I kept everything very simple, general, and I only allude to the possible extensions. I now want to go to the core of an economy. Well, let me repeat as a sort of summary. There was this attempt to find conditions on the economy that would give a unique equilibrium, and you can find a chapter of the book by Arrow and Hahn devoted to the various conditions proposed to obtain uniqueness. Those conditions are not convincing to me. if you simply require local uniqueness, that is to say, we are in our economy, we observe an equilibrium, and we believe, we would like to be able to say that it is locally unique. If it is not locally unique, then, for instance, going back to the example in the Edgeworth box, if you have a continuum of equilibria, then things are indeed very unpleasant. It means that if this is an equilibrium, you have indeterminateness in the sense that no matter how close to this equilibrium you are, you will find another equilibrium. You have fundamental instability no matter what formulation you give to your dynamical system, because if a shock moves the economy from this point to this point, since this point is an equilibrium, there is no tendency whatsoever for the economy to return to the original state. So we take this position that conceivably there are other equilibria in our economic system, but they are sufficiently far away that they are fundamentally out of reach. In order to reach them, you would have to undergo a very significant change in many parameters of the economy, which is generally very difficult to engineer, to imagine. Yes.
What is the most general form of this result? The set of
Oh, there was, for instance, after the paper that I wrote on this subject, a paper by Stephen Smale, in which demand functions can vary, as well as initial endowments. And that appeared in the Journal of Mathematical Economics. I am not sure about the year. That would be in the mid-70s, early 70s. I am quite sure the reference is in the book by Mas-Colley. Smale has written about 10 papers on the applications of global analysis to economics. That was one of the first that he wrote. Now, of course, if you have an infinite dimensional space, you can no longer use Lebesgue measure. So you have to use the concept of a residual set, for instance. Yeah. You had a question?
I thought the science theory said that the set of critical points was used at codimension 1.
So dimension 0, according to Lebesgue measure.
You measure 0,
yes.
codimension
Yeah.
1 in space.
The dimension, in the generic situation, you have, as soon as you have a Jacobian that is not of determinant 0, you can apply the inverse function theorem. And so you have local uniqueness for every one of the points there. Any other question on this matter of applications of differential topology to economic theory, which is by now a vast subject? Mas-Colley has devoted an entire book to the question, and it does not include all the results that are known. So, the core. I have talked about the core in Christchurch, but some progress has been made since my last visit, so I will mention some of them. Back to our prototype economy, we have a collection of consumers, M of them. We have L commodities. And so each one of them is characterized by an endowment vector, EI, in RL plus, and a preference relation defined on RL plus. Let me specify the assumptions I will make once for all on these concepts. They are slightly stronger than is necessary, but I do not aim at the greatest possible generality. So the preference relation, first of all, will have, as we have said in the past, will be reflexive, transitive, complete. It will have a closed graph. So far, you see, you have no strong reason to object. We will assume that the preference relation is monotone. Monotone in the following sense. If you take 2 points, x and y, in RL plus, and if you have, let us say, this strict inequality, which means that coordinate-wise you have a strong inequality. So if x is here, y has all its coordinates larger than those of x. Then we say that this implies that y is strictly preferred by the ith consumer to x. Monotone, we assume strict convexity. That is to say, if you take any x, the set of y's, at least as preferred as x, is a convex set, and moreover, the boundary does not contain a straight line segment. And I think that would be all. Finally, the EI here will be assumed to be strictly positive rather than non-negative. Why? I may hint at that later. Those assumptions can be considerably relaxed, as I will say when I present Aumann theory. And so the consumers in this economy have a total endowment vector, which is the sum of the EI. They have to reallocate this total endowment vector, and the result of the allocation will be a consumption vector x1 for the first, a consumption vector xm for the last. We will write x, the list of those consumption vectors, and they must satisfy the following conditions. xi belongs to RL plus, and in addition, the sum when I varies from 1 to m of the xi must be equal to the sum of the EI. The allocation is attainable in this sense. An extremely general problem that every economy solves in one way or another. The total resources have to be allocated to the consumers, and the allocation must be feasible in those senses. So can we exclude some of those allocations following Edgeworth, 1881, and game theorists of the 50s? We introduced the concept of a coalition, E, that is to say, a non-empty set of consumers, E, blocking a proposed allocation. That is the situation I discussed on Wednesday of last week. An allocation is proposed as the final outcome of the allocation process. Let us imagine that there is a coalition that can do the following. I am now defining blocking. E blocks S if E is not empty, surely, but if the coalition E can take its own resources, what are they? They are the summation for I in E of the EI. If it can reallocate them among themselves so that the agent I in coalition E obtains yi, can reallocate them in such a way that for every I in E, yi is strictly preferred by the i's consumer to xi. Then we say that the coalition E blocks the allocation X. Well, that is very persuasive with one qualification, very persuasive if you just have to read what Edgeworth has said and interpret it in the modern language of game theory. So I repeat, X is proposed as a tentative solution, and imagine that there is a group of consumers that notices that it can take its total resources, over which it has complete control, reallocate them among its members, and by doing so, makes every one of them more satisfied with yi than with the proposed allocation. Then there is a strong argument for those consumers to secede from the economy and to perform this operation, since it will make every one of them more satisfied according to his preferences. And so we can say that if X is blocked by any coalition, it is not viable. We are left with the set of unblocked allocations. And that, by definition, is the core of the economy script E, which we will denote by C of E. Roman C of script E. The economy E being defined exactly by those characteristics. Formally, we'll say that script E is the M list of those pairs, EI and preference relation that we have here. An example, in the Edgeworth box, two consumers, two commodities. Here is the initial endowment vector. E1 are the coordinates with respect to this coordinate system. And of course, E2 would be the coordinates with respect to this coordinate system. And where is the core? Let us draw through E1 the indifference curve for the first consumer, through E1 the indifference curve for the second consumer, something like that. Now to say that an allocation X, which is represented by X1 and of course X2 with respect to this coordinate axis, in order to be unblocked by the coalition made of the first consumer only, this point must be above this indifference curve. Otherwise, the first consumer, by using and consuming EZ1, can do better. Similarly, to be unblocked by the second coalition made of just the second consumer, the point X has to be on this side of this indifference curve. So already we are restricted to the length in between here, and there is only one more coalition to consider. Then we will have exhausted the list. It is the coalition made of the two consumers, the grand coalition, the coalition of the whole, and to say that they cannot do better by reallocating their total resources cleverly means that the allocation in question is a Pareto optimum. That's exactly the definition of a Pareto optimum. It's an allocation that is not blocked by the grand coalition. And if the set of Pareto optima is something like this, then we are left with the core, which is this set here. As soon as you have three consumers, then you have to consider all the singletons, all the pairs, and the grand coalition of 1, 2, 3. Clearly, the core becomes an extremely complex concept when you have a large number of consumers. But it is good to keep this image in mind. So much for the definition of the core in this simple context. And now I want to compare it with the set of Walras allocations. We say that an allocation X, is a Walras allocation if it can be obtained by means of a price system. Prices so far have not appeared in this discussion. So it means that X is Walras if there is a price vector so that every consumer is in equilibrium with respect to the price vector, which means that for every consumer, the Xi appearing here is best for his or her preferences in the set of Y in RL plus such that P dot Y is at most equal to P dot EI. If the price vector is P, his or her resources are worth P dot EI. This is the budget constraint. Y has to be chosen according to these two conditions, being in RL plus and satisfying this inequality. And Xi is an equilibrium if it is the best that that agent can consume. That has to be true for every I. So X is a Walras allocation if, by definition, there is a price vector for which this is true. We denote the set of the Walras allocations by W of script E. And one has the theorem to which I made an allusion that the set of Walras allocations is contained in the core of the economy. That is the theorem that can be proved with no assumptions and so simply that I will for once give a proof. Just leave this here. It's an important economic result, even if the mathematics is trivial, because it tells us that for the economy, if it has decided to use a price system, then it will end up with an allocation that no coalition can block. The converse theorem I will discuss later. It's much more interesting, much deeper, requires assumptions, but this one, utterly simple. So let us take X, a Walras allocation in W of E. By definition, there is a price vector P such that X is in equilibrium with respect to P. Could there be a blocking coalition? E. Suppose that there is, that E blocks X. I am, of course, going to prove that this is absurd. If E blocks X, it means that there is a collection of Yi such that the summation for I in E of the EI is equal to the sum for I in E of the Yi, and such that for every I in E, Yi is preferred to Xi. That is simply the definition. But if Yi is preferred to Xi, it means, since X is an equilibrium with respect to P, it means that Pyi is greater than Pei. Because if it were smaller than or equal to, it would have to be at most as desired, by definition. And if now you sum on both sides with respect to I, you have P sum for I in E of EI is strictly smaller than P summation for I in E of the Yi. But remember that we have this equality, therefore this does not permit a strict inequality here. As I promised, the proof is utterly simple and requires no assumption. So we have this result. In the Edgeworth box, you remember that we have this situation, Pareto optima, and the core is the part I stress here, where is the a set of Walras allocations. For every one of these points, you have a common tangent to the two indifference curves. You have a Walras allocation if the common tangent goes through this point, E1. And therefore, you will have here at least one, possibly 3, 5, possibly a continuum if you are in the critical situation that I discussed before. But W of E will be indeed a subset of this entire set C of E. Cannot be outside, because if you are on this side, then surely the common tangent will leave entirely below this indifference curve, and consequently the point E1 cannot go through E1. Similarly, if you were here, the common tangent would leave E1 above, and you could not have a Walras equilibrium. So we have this inclusion, which is extremely general, but in a typical situation, the set W of E is much smaller than the core. And that is an observation that von Neumann and Morgenstern in a way made. They never discussed Walras equilibria in their book. They don't even mention the core. And one can imagine why they did not, because if you take a constant sum game, then if the core is not empty, the game is inessential. That is to say, no coalition can do better than individual participants. And that made it totally uninteresting for von Neumann and Morgenstern, who were interested in constant sum games. In all the situations in which they were interested, the core would have been empty. So if they thought of it, which is quite likely, they did not consider it further. And ironically, the central concept of the book, I am now digressing, the solution concept, which is now called a stable set, has turned out to be of little interest. It's too complex, unwieldy, and it does not play a great role. They hoped that every game in their definition would have a solution. It eventually took years to come up with an example that the counterexample included, I think, 10 players in the game. You could not do it with less. And it showed that a game, according to von Neumann and Morgenstern, could have no solution after all. But this is a digression. The other very fruitful game theoretical concepts, I might as well digress my digress, have been the Nash solution, which is not in the book by von Neumann Morgenstern, and possibly the Shapley value, which of course is not either. Nevertheless, the book by von Neumann Morgenstern was one of the great moments in the history of the mathematical analysis of social sciences. For our economy E, we have shown that W of E is contained in the core C of E. And we have seen on the Edgeworth box that typically this set will be much smaller than this one. But Edgeworth already in 1881 saw a situation in which those two sets would be very close to each other, equal to each other in the limit, and that is the situation in which you have a large number of agents, and each one of them is almost or totally insignificant relative to their totality. And I will discuss this theorem in different forms in the context of replica economies, in the context of measure theory. I will make an allusion to the non-standard analysis approach, and I will discuss the elementary inequalities of Anderson and others on the divergence from competitiveness of an allocation in the core in finite economies. For the first context in which I will discuss it is chosen because it is the simplest. It is the situation of replica economies. That goes back to the treatment given by Edgeworth. Unfortunately, Edgeworth's treatment was given for two commodities and two types of consumers and could not be generalized as it was given to an arbitrary number of consumers and of types. The question treated by Edgeworth in 1881 was left completely dormant until 1959, when Shubik pointed out the connection between Edgeworth's contract curve and the game theoretical concept of the core. The next step was taken by Scarf, who generalized, who gave the first generalization of Edgeworth's theorem, and then Scarf and I gave a complete generalization to an arbitrary number of types of consumers and of commodities. And it is that result that I want to describe before we go on to a more sophisticated situation. Here you have consumer 1, and remember that each consumer is characterized by an endowment vector and a preference relation. The preference relation satisfying all the conditions I have given earlier. Here is I, and here is the m's consumer. In order to enlarge this economy, following Edgeworth, we simply replicate it. That is to say, we will have two consumers identical to each other, that is to say, with the same endowment vector and the same preference relation, two consumers having EI and the I's preference relation, and two consumers having EM and the preference relation subscript M. So we have essentially duplicated the economy, and we can do that as many times as we like. And suppose that we have replicated R times. So we have altogether R times M consumers. Let me call Q the typical row. And here you are. You will let eventually R tend to infinity. And this will be the situation that I have described already in words. A large economy becoming larger and larger, and each one of those agents becomes insignificant. That is to say, for instance, the endowment EI becomes an insignificant vector compared with the total endowment, which is the summation when I runs from 1 to M of the EI, and this is to be multiplied by R. Of course, you cannot take a ratio because those are vectors in RL, but by any norm that you can choose, this will be small with respect to that, and in fact, the ratio of the norms will tend to 0. So this is the replica economy, which I will denote by ER. And the first remark is that if you want to specify an allocation for this economy, you have to specify for each one of those agents, which is denoted by a dot, the endowment, the consumption vector x, q, I that it will obtain. The summation of the x, q, I when q varies from 1 to R and I varies from 1 to M must be equal to the total endowment for the economy, which is, as I have said here, R times summation from 1 to m of the EI. And one remark enormously simplifies the analysis. It tells you that if an allocation X is in the core of the economy ER, then all the agents of the same type, this is type 1, type I, type M, all the agents of the same type must receive identical consumption vectors. Well, that is to say, for any given I, you have xqi is equal to xq prime I, no matter what q and q prime are. And so this is the so-called equal treatment property. Which is very comforting in the sense that the agents of type I are absolutely identical with each other. Same endowment, same preferences. And it turns out that in this context, an allocation in the core will treat them identically. We have always, when we think of social systems, this desirable goal of obtaining the greatest possible equity, which can be defined in many different ways. One of the stumbling blocks is to begin with that if you take different agents, they have different preference relations. So it's difficult to say when they are treated equally. And surely, even if they are the same preference relation, which would greatly simplify matters, the fact that they have different endowment vectors would also make it difficult. But at least this is a case in which those two consumers appearing here could not be more similar in any sense. They are identical. You would expect a satisfactory solution concept to treat them identically, and this is the case here. By the way, this is proved, and the mathematical proof, which I will not give, is inspired so clearly by economic considerations that it is worthwhile looking at it. Here are the various types, and here is one R, here is all Q, and the proof would go as follows. Let X be an allocation in the core, associating with every node here a consumption vector xqi. I want to show that in any column we have the same vector. Suppose that there are some columns in which they are not all identical. For instance, in this column. Then what do we do? Since all those consumers have the same preference relation, it is easy to compare their various consumption vectors. And let us suppose that this consumer here gets the worst of all the R consumption vectors in this column. So he is treated in the worst possible way. And we do that for every column. Suppose this is the worst here, the worst here. And clearly, the coalition that has the best chance of blocking the proposed allocation is the coalition made up of those M consumers who are treated in the worst possible manner. And that is exactly what the mathematical proof does. You take this coalition and you show, using strict convexity, that it does block the proposed allocation. So the conclusion is that they have to be treated identically. This enormously simplifies the analysis because it means that to specify an allocation in the core, it is now sufficient to specify the vector, the consumption vector xi that every consumer of type I will receive. And of course, for a valorous allocation, every consumer of the same type will get the same consumption vector because they are faced with the same price vector and they are faced with their endowment vector EI, which is the same for all the consumers of type I. consequently, with strict convexity, you will get a consumption vector xi, which is uniquely determined by PEI, and therefore this is also true for the Walras, for any Walras allocation. Well, the upshot of this is that you can represent a point in what I will call CR. It is therefore the core of the economy ER considered in this space of dimension Lm. We have L commodities and M types. So CR is a subset of RLM. And we have the set W of Walras allocations, which does not depend on R. If you look at the definition here, the number of replications never appears. And we know, as we have proved a few minutes ago, that W is contained in ER, in CR. Symbolically, you have the set W and the set CR. This is the situation. It is also very easy to see that CR plus 1 is contained in CR. To say the sequence of cores is monotonically decreasing. Why is that? Very simple, because if you take the R plus 1 replica, you have already at your disposal for blocking a given allocation all the coalition that you can make with the consumers appearing in the R replica. So clearly, since you have more coalitions at your disposal with which to block, the set of allocation in the core is going to be smaller, or at worst, the same. And so you have here CR plus 1 contained in CR. And the question is now, will this sequence of sets eventually have W as a limit? In the conditions I have said, the answer is yes. And it can be phrased in either one of the following two ways. The intersection of all the CR when R varies from 1 to infinity is W. Or in the situation that we have here, those various sets are compact, non-empty. And so we can use Hausdorff distance. Perhaps you will like it better this way. The Hausdorff distance of W and CR tends to 0 as R tends to infinity. So this is Edgeworth's theorem in its general form for replica economy with L commodities and M consumers. I suppose that every one of the topics I am discussing has a moral, and the moral here is the extraordinary fact that this result remained completely forgotten from 1881 to 1959. So each one of us wonder what undiscovered treasures there are in the literature, and we cannot presume that all of us are reading more extensively than our predecessors. So I leave it to you. And it's a very simple mathematical result after all. You can prove it by using elementary arguments. Are there any questions on this replica economy situation? It is interesting to note that if you have an economy with M types, but different number of agents of the various types, the equal treatment property does not necessarily hold. There is an example given by Jerry Green, a discussion of the situation. And so, even though in the situation I have just told you about, in any given type, the agents are identical to each other, they are not going to be treated identically by an allocation in the core. Very unfortunate. You can generalize a little concept of equity, which is a very strict concept embodied in the equal treatment. in the following case. The allocation X depends on the economy, of course, which is made of the collection of the EIs and a slight generalization of the equity concept embodied in equal treatment property would be the case in which these objects vary continuously, and then you would want the allocation xi to vary continuously. That is to say, if you take two agents that are no longer identical but similar to each other, you would want their consumption vectors in any reasonable allocation process to be similar to each other, which is exactly expressed mathematically by the fact that xi depends continuously on these characteristics. Now, to say that two endowment vectors are similar, close to each other, is obvious because you are in RL plus, so you can use a concept of Euclidean distance, if you like, to describe how close they are to each other. If you want to describe two preference relations as being close to each other, then you have to appeal to the concept of similarity of preference relations that I have given you in the first lecture. You need a topology on the set of preference relations. But we have a satisfactory concept with which we can do that. Of course, the assumption of a finite number of types is restrictive, although not too disturbing for an economist, because we can think of socio-economic classes of agents, and we put together in those various classes people who are similar in the sense of having approximately the same endowment and the same preferences. And we can postulate that we have only finitely many of those. The number may be large, but finitely many. However, it would be nice if one could dispense completely with this finite type situation, and that is what Aumann did in 1964, Econometrica, and I will describe his main result. Aumann considers the agents of the economy as forming a continuum. In order to give a precise content to this idea, you need measure theory. And I will present the basic concepts that are needed. You have a set of agents A, which unfortunately will have to be infinite. In fact, its cardinality is high, but that should not disturb us too much if we accept the idea that it is a great simplification to treat a large number of units, let us say 100 million, as forming a continuum. Certainly, econometricians would not hesitate one moment to do that. Then possibly theorists can also do it. Now, if we do measure theory, we have to specify a certain set of subsets of A, the measurable subsets, and they have to form what is called a sigma field. That is to say, if you have a collection, a countable collection of EI in the class A, then the union of the EI should be in A. So the class is closed under countable addition. This will not be new to any one of us who has seen probability theory. We have a set and a sigma field of subsets. We reserve the name of coalition for the members of the sigma field, that is to say they are the measurable subsets. And then we have a measure nu, that is to say for any E in A, that is for any coalition, we have a number, nu of E, greater than or equal to 0, and nu of the total set of agents is 1, and naturally, nu is countably additive. That is to say, if we have a countable collection of disjoint coalitions, then the measure of the union is the sum of the measures of the individual coalition. Mathematically, we have here a probability space. But the interpretation is not that of probability theory. We have a set of agents, a set of coalitions, and a measure, nu, a real number defined for every coalition that is countably additive, non-negative, and nu of A is equal to 1. What is the economic interpretation of nu of E? It is the economic importance of that coalition. This is very glibly said. It has to be given some content, and we are going to do that. For instance, if you have for the coalition E a certain endowment vector, which I will call B. If you have an endowment vector B in RL plus, then you could define for that coalition nu of E as the norm of B, in some sense. So it's an a priori given real number. It's one possible definition that determines the importance of that coalition. You want a real number associated with the coalition, and that will do. Of course, you have to choose the norm in such a way that you preserve countable additivity. It can easily be done. The norm of a non-negative vector can be chosen to be, let us say, the sum of the coordinates. That's a perfectly acceptable norm for a non-negative vector. Now, in that context, where we denote an agent by small a, element of capital A, we have, of course, to define the core and the set of various allocations. X is going to be a function from A to RL plus. It does specify for every agent A in A the consumption vector X of A of that agent in RL plus. What restrictions do we put on this function X? It has to be integrable. That is to say, the integral X d nu over A and exists, and it has to be equal to the sum over A of E d nu. E is naturally a function from A to RL plus that specifies for each agent its endowment, initial endowment E sub A. Now this is the counterpart of the sum that you have seen before. Now you must work with integrals, clearly. So an allocation is that it is an integrable function from A to RL plus. It is attainable if the total demand is equal to the total supply. E, of course, again, has to be an integrable function from A to Rn plus. And what do we mean by a coalition blocking X? E has to be a coalition, an element of script A, and we ask that nu of E be strictly positive. We, as before, when we rejected empty coalitions as potential blockers, here we want the coalition to have some positive economic influence. So we rule out nu of v equals 0. A blocking coalition is an element of script A, nu of v equals 0, and it must be such that the sum over the coalition of y d nu, that is the potential reallocation of the resources of that coalition, and it must be such that you have y sub A, or y of A, preferred to x sub A, and here it won't be, of course, for every A in E, but almost everywhere in E. And so there you are. The extension from the finite case to the measure theoretical case is absolutely straightforward when it comes to definitions. You say that a coalition blocks an allocation if the coalition is measurable, is a point in the set script A, if it has a non-zero measure, and it blocks if that coalition can take its own resources, reallocate it among its members in such a way that almost every one of them, that is to say excluding a set of measure 0, you have here, YA preferred to XA according to the preferences of that agent. The preference relation satisfies all the conditions I have given earlier, closed graph, reflexive, transitive, monotone, no convexity assumption, and I will say why in my next lecture, but I just want to introduce the concept of a Walras allocation before concluding. So here is the definition of a blocking coalition. If you take the allocations that are attainable and unblocked, then they form the core. We have defined the core of E. It is a set of allocations for which there is no blocking coalition. And so before I conclude, I want to give the definition of a Walras allocation. We say that X is a Walras allocation if there is a price vector P, L components, such that every agent, almost every agent, is in equilibrium with respect to P. That is, for almost every A in A, you must have X sub A best for E's preferences in the set of Y in RL plus such that PY is smaller than or equal to P. Well, it's an exercise through which high school students could easily go to generalize from finite sums to integrals. Of course, X is attainable. It is Walras if for almost every P you have, for almost every agent, XA best for his preference relation in his budget constraint. The set of Walras allocations of the economy is denoted by W of E. Theorem 1, W of E is contained in C of E. And the proof is as simple as before. Take X in W of E. You want to show that it cannot be blocked. If X is in W of E, there is a price vector with respect to which P is in equilibrium. Suppose there were a blocking coalition E. Then you would have almost everywhere in E YA preferred to XA, and of course the sum in E of the y d nu is equal to the sum in E of E d nu. This implies that you have P dot ya greater than P dot Ea. And when you take the integral here, I'm not sure that you can see the bottom of the blackboard. If you take the integral in E, you have this smaller than P, sum of in E of y d nu, and naturally you have this equality which precludes this inequality if the measure of E is strictly positive. You see, the proof is really trivial as before. And so we have this result without any assumption whatsoever, and at the beginning of my next lecture I will give Aumann theorem, which is a statement about the equality of those two sets in a context I have not yet defined. So, are there questions about what I have said so far on the core, or about the use of global analysis in economics? As you see in the set of references, there are a number of unpublished papers which are recent, not available in Christchurch. I will leave a Xerox copy of each one of them, for instance, with Mr. Woodfield or with Frank Tay, so that you can read them if you want to. So we meet again on Friday at 3:10.